We start the stream, we share the screen, we say hello, everybody. Welcome back. We have a formative assessment to go over. Would you like to do that? I have set this up so that you can put forth another instance of this, like you can do it again if you want to use that format to take notes. I've already graded them and given you your participation points and updated the grades on the portal. So first question, how do you know what kind of conditional distribution is most appropriate for each type of categorical outcome, binary, ordinal, or nominal? What do you think? Let's do them one at a time. Binary. What distribution does binary data follow? Bernoulli. Can that be wrong? No. No. There is no possible misfit there. That's the right answer. How about ordinal or nominal? What kind do they follow? Multinomial. Can that be wrong? No. No. That's it. You don't have to worry about being wrong. This is the only cases where it's prescribed. Now, where you do have to worry about being wrong is picking the right link function. So what's the difference between cumulative and baseline categories? So first off, what does cumulative do? Because all of these links for categorical outcomes take your multi-category outcome and they divide them into a series of what I call binary submodels or subsets. The difference between the links is how they make that division. So what do cumulative logit links do? Yeah, so if I have 4 categories, 0, 1, 2, 3, then it would be 0 versus 1, 2, 3, 0, 1 versus 2, 3, 0, 1, 2 versus 3. So cumulative means that it's using all of the categories all the time. What type of outcome does that type of link make the most sense for? Ordinal. Yes. And that research questions that would lend themselves to ordinal data with a cumulative logit link. Several of you gave me good ones. Do you want to share with the group? So I'm sort of skipping into question 3 for a moment here. What kind of research question would a cumulative logit link for an ordinal variable be most appropriate? Can you give me an example?
I did the not satisfied, somewhat satisfied, satisfied.
Mm-hmm.
So there's a clear ordering.
It's clearly ordinal.
And you might want to look at the not satisfied people versus the somewhat or fully satisfied versus the people who are fully satisfied versus the people who are not fully satisfied.
Yeah, so there'd be like not satisfied versus at least a little bit satisfied. One of you gave me like C or above. Who was that? That was you, Molly? What was your example? Say.
C or above given participation in supplemental instruction.
Mm-hmm. So does participation lead to a grade of at least a C?
Yes.
Right, where you're lumping things together, but on purpose, right? Because that's the idea you're trying to map onto is C or above as a construct, or at least a little bit agree, or those kinds of things. Other examples you can think of from your worlds? Ordinal data are pretty common. Yeah, strongly agree, those sorts of Likert scales. How often do you do this? Never, once in a while, twice a week, every day, those sorts of scales. That's also ordinal. So you can predict the logit of doing something once a day or more, right, as a construct where you're lumping in the higher things. That would work. How about the other one? What kind of data/research questions would a baseline category logit be most appropriate for? So what does that one do? How does it make the binary submodels? You remember?
Just one versus another. If there's like three categories, 0 versus 1, 0 versus 2.
Mm-hmm. So one of the categories is deemed the reference. Deemed by who? You guys. Yeah, you pick. Every program has a default, but you can pick that. So you pick one of the categories as the reference. And so if I have 0, 1, 2, or 3, it's the submodels would be 0 versus 1, 0 versus 2, 0 versus 3. What kind of data does that make sense for? Nominal. Like favorite flavor of ice cream, favorite kind of pet, type of training you do after high school. Someone gave me that one. Who is that? Remember that one? Do you go to community college, four-year college, vocational school, etc.? Like those are unordered choices that you can happen. Would it ever make sense to use a baseline category link, so one reference versus each of the others for ordinal data? Could you do that? Terry says yes. You could do it.
I don't know if it's a good idea.
Well, the short answer is you can do anything, right? The software will be happy to run whatever you ask for, whether it makes any sense. But yeah, I think it could make sense. So if you wanted to be able to predict what is the logit of getting an A versus an F, a B versus an F, a C versus an F, you can have questions that lend themselves to specific category comparisons, even if they're ordinal. That's fine. It literally depends on your question, how you want to set up the submodels. Now, how about the opposite? If you have a nominal response, type of ice cream, type of pet, does a cumulative logit link make sense? No. No, then it's implying an ordering of which there is none, or at least it's debatable, right? So yeah, that's the one way you can screw this up. Take a nominal outcome and try to use a cumulative link on it. Any other permutation of those is fine. And so speaking of things to potentially screw up, what do you say to reviewer 3? So I refer to reviewer 3 a lot. Actually, I had a question in my earlier class. What do you mean by reviewer 3? Reviewer 3 is a meme because it is. You can look it up. There's videos that are unsuitable for class presentation about reviewer 3, but they're very funny. When you're an editor, usually you find people to review an article, like who you ask first is sort of reviewer 1. It's usually the person you think of as sort of whose feedback you think is most important or most relevant. And then you get down to 2 and sometimes 3. So reviewer 3 is sort of the generic term for the cranky person who is most tangentially related to what you're doing that you can never make happy. In a lot of journals nowadays, there's only 2 reviewers. And so reviewer 2 is the new meme. In fact, I belong to a Facebook group called Reviewer 2 Must Be Stopped, where people complain about stupid Reviewer 2 comments, or that, they'd made all these changes and they recommended reject anyway. It's like a venting place. But Reviewer 3 is what I'm sticking with for now because I'm old school. So what do you say to Reviewer 3 who insists that you need to fit a probit regression instead of a logistic regression? Or in the case of ordinal data, fit a cumulative probit link instead of a cumulative logit link? So there's 2 arguments. There's one that is sort of the practical use argument and another type of argument you can make based on empirical data. Most of you, I think all of you mentioned the first one, shades of the first one. So what did you say? How do you answer reviewer 3? What's the difference between probit and logit? 1.7, yes. Yep. So let me go back to, this is actually in lecture 1, excuse me. Let me find that real quick. There's a picture that I want. This picture. This is slide 15 in lecture 1. The difference between probit and logit lies in the presumed distribution of the continuous underlying response that gave rise to your observed binary outcome? Yes, those faces, exactly. It lies in the presumed distribution of the continuous underlying response that created your observed binary variable. If you believe that the continuous underlying response is logistic, it has a variance of 3.29. If you believe that your continuous underlying response is normally distributed, that's probit with a variance of 1. And if you take your probit coefficients and multiply them by 1.701, I think is the you can go many decimals out. This is the difference in what the model predicts. So numerically, it is unlikely that you would find different results in one versus the other. The way that you can test that, though, is that different link functions, you can look at AIC and BIC to see which one is smaller. There is no cutoff. Smaller is better. There's no significance test. So you can look at AIC and BIC to see if it cares. Both of these links have symmetric predictions above about 50-50. They do the same thing versus other links. The slide right after it, log-log and complementary log-log, those are actually different. And again, AIC and BIC to decide which one fits better. But practically speaking, logit is the only one that gives you odds ratios. They don't exist because the others aren't based on odds. So I would say a complete response would probably mention that these differ in scale. They both have a symmetric prediction. You might point to AIC and BIC, and because you want to provide odds ratios for effect sizes, that lends itself to the logit instead. So a probit regression is the combination of a probit link and a conditional Bernoulli distribution. A logistic regression is the combination of a logit link and a conditional Bernoulli distribution. And it really doesn't matter. When we get into multivariate models, the way that you choose to estimate the model may force you into choosing one of these versus the other. Full information maximum likelihood has both options in a lot of software, whereas limited information maximum likelihood only has probits, that probit scale. So you may end up stuck back in probits, which is the main reason why I present it in the first place. Okay. So, questions on that? So the two sets of decisions that you have to make in this world of generalized models. What kind of link do you need? What kind of outcome distribution do you need? They're orthogonal, although they tend to go together in practice. Outcomes that are bounded on both sides, so categorical data, for instance, or if you have a 1 to 5 ordinal scale, you can't go past 1, you can't go past 5. That's what logits and probits and such are for. We started talking about counts, which is bounded only on the 0 side, and people use logs for those. Also inverse link, 1 over the mean is another one that shows up, but less commonly so. Counts are much trickier because you have to figure out what distribution goes with them. Then you can actually be wrong, unlike categorical data. So, other questions on any of this? All right. Questions on homework 2 yet? Not yet. Okay, that's fair enough. So we started talking about counts last time. You want to go back to that? Why not, right? So we have our new friend, the log. The job of the log link is to keep the predicted counts positive. So we predict the log of the expected count with a linear model, same as usual. The tricky part comes in what kind of distribution goes with it. So we looked at a couple options. One was Poisson. This one is really restrictive and rarely fits in practice because it says the mean is equal to the variance. So note that it is a non-constant variance. Like if your predicted mean is 10, the predicted variance is 10. If your predicted mean is 4, the variance around it is 4. So there's 3 potential problems with Poisson. Too much variance, usually, sometimes not enough, but almost always too much. Whether or not whether there's any zero values and whether there's too many zero values. And the fix to the first one, too much variance, is to turn it from a Poisson into negative binomial, which adds an extra stretchy factor that allows the variance to exceed the mean in a multiplicative fashion. So this extra k thing, that's the difference. It multiplies the mean squared. And we can do a likelihood ratio test to compare the fit of Poisson versus negative binomial and decide whether or not we need this extra k stretchy factor. And so I think that was about where we started looking at the example. We have a new rubric that we can use to decide if our distribution fits, which is this Pearson chi-square over degrees of freedom statistic that compares the observed residuals and what their standard deviation would be to what it actually is supposed to be according to the model. And so ideally you want these things to match so the ratio goes to 1. So we started looking at this real life example. So this is from a master's thesis of a former student at the University of Nebraska. It was a ANOVA type 2x3 design where we have participants with or without a history of interpartner violence, and they were randomly assigned to one of 3 conditions, and they were asked to do some sort of relationship-related interaction with each other, and they were either taught not to have any strategy in dealing with frustration, cognitive reappraisal, or suppression. So that part is between groups, as is the IPV variable. So this is basically 6 different groups of people that we're talking about. I thought this would be a good chance for us to go back over interaction terms too. How about that? Will that help? Yes. But guess what? There's none on your second homework. Because proportional odds and non-proportional odds I thought was hard enough. But it's good for us to be able to go back over this. So here's the outcome. The outcome we're looking at is number of mean things said, aggressive verbalizations. Looks like there's a whole lot of people who didn't say anything mean, and then a big positive skew of meanness, culminating in someone who said 24 mean things. Here are the cell means, unadjusted, just from the raw data. In the model, these are going to be controlled for performance in a neutral condition, but that covariate didn't matter much, so these are pretty much the means. And the question is, you can phrase it either way. Is the difference between people with and without IPV different across these strategy conditions? Or does the effect of strategy differ for people with or without interpartner violence? So the first interpretation, does the difference between, as a function of IPV, differ by strategy? That is the vertical distance between these points on this graph. And it kind of looks like it. There's just eyeballing it, it looks like there's a bigger difference between the lines for the suppression condition relative to the other 2. The difference is actually backwards in the cognitive reappraisal, and there's not much difference in the no condition. The other way to look at it is the difference along the lines. So for instance, if I go from no to cognitive reappraisal in blue, is that slope the same as the slope going from no to cognitive reappraisal in red? And we could go from cognitive reappraisal to suppression and look at those differences in slopes, or no versus suppression as well. So those are the simple effects that we'll be interested in exploring to try and describe any potential interaction. It looks like the model itself, based on this picture right here, so this is the distribution of the outcome within each of the 6 types of people. After you know what type of person you are, you know one's tendency to say a 0 or not. So this extra 0 tendency right here is mostly explained by the model. We'll see how that works empirically later on, but we can look at pictures to sort of anticipate what's going to happen. So first model to compare with, it's fine. Let's just pretend it's normal. Because that's what I know how to do. So here's my model. I'm using GLM, which this right here, link identity family Gaussian. That's what you know of as general linear models. So that is regression, ANOVA, ANCOVA, independent t-tests, all that stuff. That's identity link, meaning no transformation of the predicted outcome, and family, normal, Gaussian. The analog in SAS is link equals identity, dist equals normal right here. So that's the part that's going to swap in and out as we look at different models. In terms of the coding scheme, I treated ER condition, so emotional regulation condition, that's the strategy condition, as categorical. I set the last group to be the reference so that the output would match with SAS. IPV I'm treating as continuous. It's just 0 equals no and 1 equals yes. And neutral is also the same. I'm treating that as continuous as well. That's just a covariate that does not interact with the IPV or ER condition variables. Okay. This thing right here, what's that doing? Feel free to read from the comment right above the line. This is your multivariate Wald test. It's the analog to the F-test that goes with your model R-square in regression. We don't have R-square anymore. It's gone. But we still have a test of it functionally. Whether your model is significant, whether these things work together to have some sort of prediction that's better than no prediction at all. So I'm saying combine this slope being 0, that slope being 0. These two together say no group differences across the three categories of this variable. Likewise, the interaction of IPV with group. These two these are the interaction contrasts. There is a contrast statement you can use to get the simple main effective group, which is conditional in IPv 0, given the way the model's set up with the continuous covariates, as well as the interaction term. So Wald tests come in two flavors, right? Univariate, multivariate. Univariate means you're testing one thing. Like that's what shows up on your output. You have your parameter, the estimate, standard error, either a t or a z and a p-value. That's univariate, testing one thing. If you want to test more than one thing at a time, you have to ask for it. And so this first one is saying, does my model work together to predict something? These are being more specific. They're lumping together the two contrasts for the interaction of IPV by condition, as well as the main effect of condition. Let me see here, one person is waiting. There we go. Welcome, one more Zoomer. Those are what's known as your omnibus tests that you'd see in an ANOVA output. So this is the analog to that same idea. Margins in Stata, I dot. So I'm asking for the group mean at each level of this categorical variable. I am asking for it conditionally at these levels of the covariates. So this is what's known as an adjusted mean. It's holding neutral constant at 0 and holding IPV constant at 0. So that's how I would get 3 of the means. The second statement then continues to hold neutral constant at 0 and switches IPV to be 1. And that gets me the other 3. Okay. With me so far? All right, let me go down to SAS and do that much. Contrast statement. That's how we get the analog to the R-square F-test. I'm lumping everything together. Question?
Don't you have to have another contrast of 2 and 3 in order to examine one?
Nope. So those two statements right there, that's group 1 versus group 2, and group 1 versus group 3. If I know those two, I know 2 versus 3 is a linear combination of those.
Is you add it, it wouldn't change anything.
It may mess it up, or else it may give you an error. I'm not sure what it would do. So if you have a 3-group variable, you need 2 predictors in the model to differentiate those 3 groups, right? This is the analog. I need 2 differences to be able to recreate all 3 possible differences. It doesn't matter which differences I put here. So I could do this instead. Doesn't matter. So long as they're 2 different differences, it'll figure it out. Same thing with this interaction term. Whenever possible, I try to set up my model so that only one predictor is categorical at a time. That way you don't end up with like a string of values that you have to figure out what they are. So I'm treating IPV as continuous in this case. That way the interaction with the categorical variable takes the exact same form as its main effect. So those 2 together make up the group by IPV interaction. It gives me 2 of the interaction contrasts. I can get the 3rd as a linear combination. I don't have to ask for the omnibus main effect of group separately here or the omnibus interaction separately here, because that shows up by default in SAS once you denote a variable as categorical. So that's one extra piece. And then margins, the analog here is ls means. Ls means is only available if you denote a variable as categorical. So I'm asking for the model estimated mean at each level of ER condition, at holding these 2 variables, the covariates constant at the values in parentheses, in the order. So it's neutral equals 0, IPV equals 0, neutral equals 0, IPV equals 1. And adding confidence intervals too. Okay. With me so far? All right. Now the differences. I am going to copy this text and open up a new page. Layout. I need small margins. There we go. And I'm also going to steal the model equation and copy this too. So to figure out how these groups differ from each other, 2 sets of simple effects. What is the effect of strategy condition for each type of IPV? What is the effect of IPV for each strategy condition? So if I want the simple effects of condition per IPV, so I want condition. How do I get that? What's step 1? How do I find the simple effect of condition for any type of person? Strategy condition, specifically. What do I do first? Strategy condition simple effect equals. Wherever it's listed. So I need those 2. And I need those ones. Okay. That unit right there is the basis of each of these statements. Those 4 terms show up in every single one of the next 6 lines. So if I want the difference between none and cognitive reappraisal, then I want the difference between group 1 and group 2. So in Stata, it's I1 and I2. So this is group 2 minus group 1. Now, what kind of person do I want that difference for? IPv0. So the values that get plugged in here are the values of the moderator, IPv. If I want it for IPv0, they zero out. In contrast, if I look at this line, this starts the same way. It starts with the difference between group 1 and group 2, but now I want it when IPv equals 1. So I take that pattern of coefficient for the group differences, the -1 and the 1, I multiply it by IPv1, and the interaction terms turn on. So in terms of the picture that we have, what I have highlighted right now here's my picture. Here it is. It gives us the difference between the none and cognitive condition. So the slope right here, can you see my cursor? It's these two slopes. That's what I've asked for right now. Whether those slopes right here are different than 0. That's what I got so far. Okay, are you with me? Okay. Same thing in SAS. Go back to the other handout. Looks like that line and that line. -1 for the first group, 1 for the second group. The interaction term zeroes out if it's for IPv0. The interaction term takes on the same values as the main effect because they're being multiplied by IPv equals 1 to create the interaction. Why we don't have beta 2 for which one? Because what we're asking for is the effect of condition.
Oh, condition.
Yeah, strategy condition. The none versus cognitive reappraisal versus suppression, that 3-category variable, we're asking for none versus group 1 versus group 2, we'll say. I want it for somebody with IPv equals 0 as the moderator, but the main effect of IPv has nothing to do with it. So in general, when you're trying to find how the model gives you a simple effect, the only terms that are relevant have to have that simple effect in them.
A quick question about the SAS code.
Sure.
In the model part, you said that whatever the sequence of the comparison, we only need 2 sets of comparisons for one 3-category variable. And in the simple index of condition part, when you do the comparison, how do you know the sequence between the -1 and 1, such as the non and cognitive? You use the comparison for the first and the second. How do you decide the sequence of those comparisons?
How do I know which group maps onto the numbers?
Yes.
2 ways. If you have no idea, do that. Put a /e, and it's going to give you a table of groups, and it will tell you in the table where your 1s and 0s went. But I know this because it's in the order in which it shows up in your data. So in this original variable, 1 is none, 2 is cognitive reappraisal, and 3 is suppression. And so I know that this place refers to whether or not you want to invoke the none group. This place refers to the second group, and this refers to the third group. And it is either alphabetical or numeric. If you have labels, it switches to alphabetical, which is why when I made my labels, I put the number in front. because otherwise it would rearrange them so that cognitive would be first and none would be second, and I would lose my mind.
So the values will be, the categoricals will be named kind of ordered sequentially by their names.
If you don't put labels on them, then it's just numeric. Group 1, group 2, group 3. If you put labels on them in SAS, it reorders them to be alphabetic. And so I am overriding that tendency by sticking the number inside the label so that the order stays the same. I don't know if Stata does that to you or not. You'd have to find out. I don't think it does because there's no point in Stata where you give it like a series of values for that until you get down to contrast. But that would be something to check. Good questions. Sure. Where were we? Hadn't made it that far yet. We're still decomposing the code here. Okay. So the other simple effects then, group 1 versus group 3. That's that and that. And then I turn it on if it is for IPV equals 1. Copy the same pattern because it's multiplied by 1, and IPv0 is right here. The last but not least, 2 versus 3. So note I'm changing the numbers. So this is 1 versus 2, 1 versus 3, this is 2 versus 3. And the only instances in which the interaction terms take values is when it's IPv equals 1. So it's being treated as a continuous covariate that multiplies those values. Okay. Now going the other way. Back to my picture. What I have asked for are the slopes going from none to cog, from none to suppression, and cog to suppression. The other ones I don't have yet are the vertical differences between these lines. What is the difference as a function of IPV? So to get those, what do I need? IPV simple effect equals. Which terms in my model do I need? I need this one at a minimum, beta 2. Let's grab that. And what other ones? 5 and 6. So I have the implicit times 1 missing on here, I think because I was probably running out of room. But I'll add those. So simple effects of IPV. At a minimum, you need one of these, right? Now who do you want it for? What group? Yeah, so for the first one, I want it for group 1. I want it for group 2. I want it for group 3. That's the vertical distances between those lines at each point there. And analogous in SAS, IPv1, in each case, that gives me 1 beta 2 plus which group do I want it for? So group is the moderator. I'm saying 1 if I want it for that group and 0 if I don't want it for that group. But we're not done yet. So we have basically all pairwise comparisons of interest right now. That's what we've got. But that doesn't answer the interaction question. Interactions are differences of differences. Does the effective IPV differ by strategy condition? Does the effective strategy condition differ by IPV? Two alternative ways of asking the same question. That's your interaction terms. So that tells you the extent to which the effective IPV differs between groups 1 and 2, groups 1 and 3, groups 2 and 3. It also tells you the extent to which your group 1 to 2 difference differs as a function of IPV. Either way. In Stata, there are contrast statements that look a lot like SAS. So this is the only instance in which you see the same pattern of 1s and 0s. The interaction contrast of group 1 versus 2, group 1 versus 3, and group 2 versus 3. So this part that we just went over is completely the same, whether you're in normal land, Poisson land, log land, logit land. You just have to know what you're predicting in terms of, is it the log of the count, is it the logit of the probability? But this logic of getting simple effect and simple effect differences works the same way regardless of what kind of model you have. All right, how are we doing? All right, let's see some numbers. Now, which set of numbers do we want to interpret? The ones that actually fit. So here is, this is the part that we looked at before. This is the output from SAS for the ANCOVA model, assuming the residuals are normal. Here's our chi-square over degrees of freedom test of our residuals. What should that number be? Yeah, feel free to read from the screen. Yeah, 1. Is 11 1? No, probably not. So indications that this doesn't fit come from our confidence intervals around each of our condition means. Can I have a negative 0.08 number of mean things said? No. So the model is predicting things that can't happen. That's not good. So we're not going to look at these estimates because we don't trust them. Next, how about Poisson? So the difference in terms of the model is right here. We're predicting the log of the expected count, not the expected count. Everything else is the same, but note that I don't have an E on here anymore because residual variance is not a thing. The Poisson distribution says the variance is the same as the mean, which means the variance and the mean change. So there's less variability around smaller predicted counts, which makes sense because they can't go past 0. The only thing that's different in terms of the code is that I'm explicitly asking for 2 different kinds of margins, or LS means. I want them in the model metric, the log count, because that's what the significance tests are going to be looking for differences between. And then I want them in the original count metric, the data scale, so that we can actually talk about them as real numbers that we know what they mean. Everything else is the same. All of these simple effects, tests, and interaction contrasts are on log count, model scale. To change the model, here it is. Link log, Poisson residuals. There's also, instead of a GLM, there is a Poisson version that you can go to directly in Stata. It doesn't provide the Pearson chi-square fit statistic though. So here's some Stata output. In GLM, Stata helpfully tries to remind you what you've asked for. So the variance in this model is supposed to be the mean. How are we modeling the mean? It's the log of it. Our value of 11 for how well the residual distribution fits has gone down to 4. We're headed in the right direction, but I'm not there yet, not happy with this. So analog in SAS, link equals log, dist equals Poisson, same idea. Adding iLink here on the LS means to get log counts and irregular counts. Note that already our results are changing. This was a p-value of 0.06 for the interaction term in the normal model. It's changed significantly. But we're going to keep going. Negative binomial. The role of negative binomial is to allow the variance to exceed the mean. Why did I think negative binomial would be a good idea? Because of how skewed this thing is. The tail that stretches out to 24 mean things. That's why. So in Stata, I am switching temporarily to the nbreg command, which is negative binomial regression. The reason I am doing that is because it gives you the scale factor right here. And it gives you a likelihood ratio test as to whether that scale factor is 0. So it does the work for you of deciding if Poisson is good enough or if you need negative binomial. In Poisson, this alpha thing, this k stretchy factor, would be 0. It's not 0. It's 1.6. And 1.6 is not 0. Chi-square of 327. So now that we know that we need it, I'll switch back to GLM so that I can see how well it fits in an absolute sense. Still in the log link, still predicting the log of the expected count, but now family is n binomial. The ML means that you're letting it estimate the k stretchy factor as opposed to putting a value there yourself. In SAS, this version gives you exponentiated versions of the slopes, either E form or IRR. Those are effect sizes and an odds ratio type metric. And log equals link and dist equals negbin in SAS. And this is where I think we left off. I was celebrating victory. 1.1. I've never actually seen it that good in real data before. Normally I have to make up data for it to get to be that good. But the new model says the variance is still a function of the mean, but there's an extra term that allows the variance to exceed the mean. It's a quadratic function instead of just a straight one-to-one mapping. Now we can interpret the results and have some confidence. Okay. So, who's my reference group? The log of the expected count of number of means things said is 0.85 for what kind of person? Someone with neutral of 0, meaning they didn't say any mean things at all in the neutral condition. How about relative to IPV? When IPV is 0 or 1, now remember, I'm treating IPV as if it were continuous, meaning 0 is really 0 and 1 is really 1. So who's my reference person according to the model? 0. So what does an IPV of 0 mean in this context? The variable is referring to whether or not you have a history of interpartner violence. 0 means no history. Now how about ER condition? That's my strategy condition. Who is my reference for that variable? Yes, suppression, group 3. And I know that because in SAS, the last one is always the reference. I switched it to be that way in Stata so the output would match, but I know that steering here because that's what the dots mean. There is no effect of number 3 because their conditional mean is already given by the intercept. So somebody without a history of interpartner violence who said no mean things in the neutral condition and who was put into the suppression strategy condition has an expected log count of 0.85. Relative to that kind of person, these two terms right here, those are simple effects of strategy. Because of the interaction terms that are forthcoming, those interaction terms make these conditional on IPV equals 0. So these two lines right here give you the group differences due to strategy, specifically in people without a history of violence. Let me try to split this so that we can see the picture, because I think it's helpful to map that back. Picture of means is right here. They're going to be very close but not exact for the picture because of the adjustment for the neutral condition. There we go. There's my picture. So the "you are here" sign for the model. The 0.85, where's that on my picture? Yeah, the blue is no, red is yes. So right here. Relative to this kind of person, I am tracing along the blue line. So relative to the suppression condition, people assigned to the condition number 2, cognitive reappraisal, are lower. Slope is negative going this way here. Significantly lower? Yeah, here's my p-value. It's the second to last column. Yep. So it looks like people who were told to suppress their feelings said more mean things. Don't keep it down, let it out. Yeah, there's my clinical psychology interlude for the day. How about people who were not told to do anything special? So this blue dot versus that blue dot. Not significant. The no people are slightly higher, but not significantly higher. So note that I'm just referring to this pattern, this picture to get your pattern. This is in counts, whereas my numbers down here are in log counts, but you can still think of the direction as smaller or bigger. Okay. Now the interaction terms. And highlight these things. The first two rows that are highlighted are the effects of strategy in people without a history of IPV. So if I look at the 2 group, for instance, the effect of strategy is negative. People in the reappraisal condition say fewer mean things. How does that tendency change in people who have a history of IPV? It becomes what? And your choices are more positive, less positive, more negative, or less negative. More negative, which means stronger or weaker? Which is it? More anything. More anything is stronger. Yeah. So we're talking about the difference between the slope of the blue line going from suppression to cognitive reappraisal and the slope of the red line going from suppression to cognitive reappraisal. The red line has a more negative slope starting from suppression. Significantly so. Likewise, we looked at the difference between this little blue dot and this blue dot. Now we want to know if that difference differs from this red dot to this red dot. That's going to be this one and that one. What do you think? So there's a very slight positive effect that's not significant in people without IPV between suppression and no instruction. That tendency becomes what in people with a history of IPV? This one's tricky. Yeah, I'd be saying less positive, but really it's like you're going from 0 down to something negative. It's backwards, right? The blue line is higher slightly in the none condition than in the suppression condition, but the red line is much higher in suppression than in the none. They're backwards. So the effective strategy, none versus suppression, differs as a function of IPV, but to a non-significant extent here. Here's my p-value. Now, does that surprise you? It looks like there's a bigger difference between these red endpoints than the blue endpoints if I'm just staring at this. But what is not on my picture that probably should be? Variance. How would I show variance on my picture? Error bars. Yeah, we don't have any error bars. So the bigger the value, the more error there is around it in these models. That's the way that it has to work. So we only have a select subset of all the possible differences. The model gives us only some of them. Question?
Actually, I have a question about how you got that picture. So did you just take the values and like use Excel or something?
This is an Excel picture. Now this picture is a descriptive thing. I literally took the means in the data set of the count and I made a picture. The ones that are predicted by the model are not going to match exactly for two reasons. One is that the model is predicting log count and then you have to back transform into raw count, and that transformation means they're not going to be exact. The other reason is because this picture is not conditioning on the neutral as a covariate, whereas the model is. But how would I make a picture that's model-based? Is that going to be your question?
Well, I guess just if you were to do this for a publication or something, how
Mm-hmm.
would you choose what to present?
Great question. So I have this model that tells me what all the cell means are. Wouldn't it be nice if it did the math for me to figure out what the cell means are based on all these differences? Wouldn't that be nice? Wouldn't it be nice if it did it for me? Then I wouldn't have to write so much. Ta-da! Margins and LS means.
Can I ask what does that zero do?
What does what do?
That zero.
The zero?
No, CL.
CL. Oh, confidence limits, confidence intervals. Yep. So let's go get my means. And in Stata, what's the analog to this? Stata's command is actually more flexible because it can do it for any kind of predictor. It's margins. So let's go see what the means are. Let me squish the top a little bit more so I can make my screen a little bigger. Here they are. So, estimate is mean in the model scale. So does it look weird to you that this number, for instance, is negative? Is that fine or is that weird? Can I have a negative count? No. Can I have a negative log count? Yes. Which is this? This is log count. Estimate is a model-based mean. Predict XB or model predicted log count. Because I asked for confidence intervals around that model predicted log count, the table went on to another set of lines. But here is this mean column. That's the result of I-link, the inverse link back down to predicted counts. So here are the actual counts. More importantly, look at the standard errors next to them. They differ wildly because standard errors are tied to the mean itself. They grow with the mean in a quadratic fashion. That's the model. So there is no more such thing as homogeneity of variance in these models. Counts of near zero can't have the same variance around them as counts of 10. They can't. So a predicted count near zero, like this one, has a tiny error around it, whereas a predicted count of 2.5 has a lot more error around it. The other differences across these standard errors, besides the fact that the means are different, is the sample sizes are different. So they tried to assign people equally to the strategy groups, but in terms of the proportion of people who came in with IPV, there's a lot fewer of them, fortunately, right? So yes, to answer your question, these are the means that go in your paper. This is how you make your error bars around them. Okay. The other things that we would want to look at. In SAS, we get multivariate Wald tests for any variables that are categorical, including the simple main effect of VR condition at IPv0 and the interaction contrasts. Those are the things you had to ask for via contrast in Stata. The thing I did ask for, multivariate Wald test for the model, that's the analog of the F-test in a regression for the model. And then we get into the simple effect differences. So the first three are the effects of strategy within the no group. So people say more mean things in the cognitive reappraisal group relative to neutral if they have no history of violence. They say more mean things in the suppression group than the cognitive reappraisal group if they have no history of violence. That's the blue line here. There's no difference between none and suppression. That's along the blue lines. The differences along the red lines are right here. So we have 3 fewer log counts in the cognitive condition than the none condition. We have about 3.3 more log counts in suppression versus cognition, and the difference between none and suppression is not significant. The last column here, these are your odds ratio like things. It's e to the that. So if this is your slope, e to that slope is over here. They're called incident rate ratios, but they're the same thing as odds ratios in terms of how you would interpret them. Then we have the simple effects of IPV, so the differences between these lines that we asked for. So for the none condition, there is a difference or no difference? No real difference. For the cognitive reappraisal condition, this one right here, who is higher? Blue, which is IPV no. The coefficient is negative, meaning the yes group is lower. And out here are these two different. Trending. P-value of 0.09. Yeah, traditionally, no, they're not different. And that's where you need the error bars, because it looks like they should be, but they're not. Then we get the interaction terms. So the difference between those two numbers right there is right here. So if you want to compare none versus cog, is this vertical difference different than that vertical difference? Survey says, yep. This one is significantly more negative. If I want to compare the difference at none to the difference at suppression, are those differences different? Nope. And then last but not least, cognitive difference, suppression difference, are those differences different? Yes. Now we got the story. Interaction terms that have more than one degree of freedom. You have to be able to reduce it down to single degree of freedom contrast like this. So the interaction term itself in the model requires two terms. You can always get the third as a linear combination. Now, are we done yet? Well, we're done with class in like 3 minutes, but is this done yet? No. I wanted to check for more than one thing, whether or not I still have too many zeros. So whether or not we need zero inflated versions of these models, Poisson and negative binomial, that's where we will be next time. It looks like next time we might finish a little bit early relative to what I had planned. If that happens, I'll give you the rest of the time to work on your homework. Your homework is not over this. Your homework is over categorical outcome models. And I did check. I was able to install Go Logit 2 inside the virtual desktop. So those of you who do your homework that way will be able to use that just fine. If you do have any problems related to that, let me know and I'm happy to help you troubleshoot. Okay? All right. Questions on any of this stuff? As usual, the end of this handout, 2 more models, has words. So lots and lots of words. You can also see how the words turned out in the original publication, which I have put up a link to right here. So, and you can see the influence of reviewer 3 in changing just little bits and pieces here and there. So, all right, office hours start now. Let me know if you need anything. Otherwise, I'll see you Thursday. Yo.